Um, Welcome back to another pulse session, everybody. It is a pleasure today to have Victor Reis previously from the University of Washington and currently at the Institute for Advanced Study in Princeton, who will talk to us on the subspace flatness conjecture and faster integer programming. Victor, the floor is yours.
Thanks, Beatrice, for the invitation. I'll talk about some joint work from my PhD advisor, Thomas. So here's a brief introduction. So the problem we're going to be solving is, so we're given a convex body K in n dimensions. And our goal is to either find a point of integer coordinates inside it, or to certify that there's none. So this is a classical problem in computer science. And well, it's known to be NP hard since the 70s, because, for example, if you're familiar with the satisfiability problem, like 3-sat, this is a generalization of this case. So that's known to be NP hard. There's also an algorithm known when the dimension is fixed that runs in polynomial time. Like n here is the dimension. So Lenstra showed in the 80s that, if the dimension is fixed, that you can do it in polynomial time. It's 2 to the n squared. This was later improved by Cannon to n to the order n, and there's also other small improvements by the Douche and others. So I'll give a brief sketch of how the Douches and all of these algorithms essentially work. So essentially the high level idea is the following. So we're going to slightly generalize the problem. So in the previous slide, we were working with the integer lattice. Here we can generalize it for any discrete subgroup of Rn, meaning like any linear map of the integers. And here the goal is to either find a point in the lattice that is also in the convex set, or tell there is none. So the idea is going to be as follows. So the first step is, if the body K is going to be too large compared to the lattice, meaning that any translate of my convex body contains some lattice point. Well, it's not so clear how to certify that, but we're going to talk about that later. Then we shrink K a little bit, because if I superobserve this property that any translate contains an integer point or a lattice point, then I can still make it a little smaller, and if that's still satisfied, then I won't lose anything. Notice that this first step also is a reason why the algorithm only finds a point and doesn't enumerate all the points. So this might lose some other points, but as long as there's still some left, then that's okay. And the second step is we're going to find some subspace W. In this case, it's just this line, for which once we project both the convex set and the lattice onto the subspace, there won't be too many points left. So here's the points. So the idea is that like any lattice point that was originally in the lattice, well, in this case, there's none, but like any point that would be in the lattice to begin with, once I project, it's still in this intersection. This raises the question of like, how do I find the subspace? Well, we're going to talk about that later. And the third step is to enumerate all the points inside this intersection. Well, I'm also not talking too much about that. It's also like a part of Douche's algorithm. Essentially, it uses this convex geometric tool called M ellipsoids. And then we're going to recurse on all these fibers, meaning like all these pre-images of the projection. And it turns out that if you do this with like a careful choice of the subspace, this will lead to a order n to the n runtime. That was the known bound before. Lenstra's algorithm was also similar to this. The key difference there was that Lenstra only chose a hyperplane for W. So here, the Douche has a general choice of W that he chooses carefully. Lenstra's algorithm only picked a hyperplane. So I'm going to be talking about like how do we know what is too large, and like how do we find the subspace W. So here the key tool we're going to be using is this covering radius. So given a convex body K and a lattice L, the lattice will be defined by the basis B. It's going to be denoted as a least radius, for which I can put a copy of K in every point of the lattice, and we'll cover the entire space. It turns out that there's an equivalent definition of this by using the fact that the lattice and the space are both symmetric, it's equivalent to saying that, for every point of the space, I can put a copy of the convex body such that I always intersect the lattice. So here's the covering radius. It turns out that it's the same thing as putting copies of the body in the lattice points and covering the entire space. And this doesn't use it's like for any convex body, it doesn't have to be symmetric. So this quantity, it's not so clear how to compute it. It's not necessarily an NP or co-NP. So we're going to be looking at some ways to approximate it. So here's a classic lower bound on the covering radius. So given a lattice, we're going to have a measure of how dense the lattice is. So given the basis B, we're going to define the determinant of the lattice to be the volume of this parallelepiped spanned by the basis. So this is kind of like the inverse density of L. The larger the determinant, the more sparse kind of the lattice is, the less dense. And then there's a way to lower bound this covering radius based on the determinant. And the point is that, well, any point that covers the entire, any convex body that covers the entire space when put in the, when put as translates in the lattices, well, the volume needs to be at least a determinant, because the determinant, the volume of this parallelepiped, is like a fundamental domain, meaning that if I take copies of this parallelepiped on every lattice point, do exactly cover the space. Therefore, any convex body that is placed such that it covers the space needs to have at least as much volume. And that's why this lower bound follows. Well, but this lower bound is not necessarily very tight. For example, in this case, if I put translates of K on every lattice point, it will look like this. Well, there's a lot of overlap. So this bound is not necessarily very tight. However, we do have a way to make it a little tighter. Well, one thing we can do is we can pick a subspace, and we can lower bound the covering radius by projecting onto the subspace, because every covering of the original space, once I project it onto W, it's still a covering of W. So we also have this lower bound that works for every subspace. And our main theorem here is going to be that this lower bound is actually much tighter. You can see that the original lower bound, when you just take the W to be the entire space, it can be arbitrarily bad if the K is very flat. It turns out that this lower bound using a general subspace is tight up to a polylogarithmic factor. So this is our main theorem. So we define the covering radius again as this smallest radius so that I cover the space. And the claims that there's a subspace for which this approximation I described in the previous slide is tied up to a log cubed factor. We don't know how to compute this subspace W exactly. So if we want to transform this into an algorithm, we have to pay another log factor. And following the previous algorithm of the douche, it implies that we can get an algorithm for integer programming log n to the 4n time. So I'll explain how the proof works. So I guess the first step of the proof is that, well, we want to approximate this covering radius, so we need some upper bound for that. And an idea we have is to take a triangle inequality for this covering radius. So the idea is that, well, if I can take a subspace U, well, I don't know what this U is going to be at, but the point is that I can always split my convex body in my lattice into a section and a projection. So this is kind of like a triangle inequality sort of thing. And the thing why this is helpful is that, well, if I can make sure that the dimension of U is large, say at least like constant, like a constant fraction of n, like n over 2, then well, I can do some induction, because the second half, the second part, which is a projection, well, it kind of meshes very well with the definition of this lower bound above. And the point is that this lower bound for L and K, well, like you can easily relate it to the lower bound of the projection. The difficult part is how do we deal with the sections? And for this, we're going to need to find a nice chain of these lattices. Basically, like we need to find a bunch of lattices, one containing the other, and we're going to take this U to be the span of like half of them, essentially. And here, well, I'm skipping one part, which I'll come back to later, but like before we find this chain, we're going to need to put K into like some nice position. So we want to make sure that K is like approximately well-rounded before we do this, and that this will also make the lattice a little look different, because for example, if I start with like the integer lattice, it turns out that this chain will be trivial, but once we apply some linear transformation, this chain will look more interesting. And I guess that any linear transformation applied to both K and L will preserve this lower bound above, because both the determinant and the volume behave well with linear transformations. So first, we're going to be talking about like what are these chains? How do we kind of write out some nice decomposition of lattices? So we're going to need this definition of a quotient lattice. So given a lattice L, the lattice L in this case is just the z squared, the black points. If I have a subspace L prime and I take the span, the quotient lattice will be essentially projecting onto the orthogonal complement. So this is a very useful kind of decomposition of my lattice, because, for example, I can be verified that the determinant of L is exactly the determinant of L times the determinant of the quotient. And so the nice thing we're going to be needing is this canonical filtration. Well, if you haven't seen this yet, this is a little unintuitive at first. So the idea is that we're going to plot every sublattice of L in a 2D graph. So essentially, like every point here represents a sublattice. And we're going to be taking the lower envelope, like the convex hull of all these points, which are I take the rank and the log of the determinant and I plot it into this graph, and I take the lower envelope of these points. And this would be the canonical polygon. So why is this interesting? The point is that these vertices of this convex hull will exactly be a chain. So here's the precise claim. If I take this, so L0 will be there's only one sublattice of rank 0, which is just the origin. And there's only one sublattice of full rank, which is L of rank n. But there may be like several, in the middle, there may be several. And, like not every rank will have a point in the vertex as a vertex of this convex hull, but that's fine. That's why I have LK here and not LN. Like this K might be much smaller. For example, like if L is the integer lattice Zn, there's only like a single line in this image. It's just 0 to Zn. But the point is that there's this canonical filtration gives a nice chain, a decomposition of this lattice. This is not obvious at first because I just defined it to be the vertices of this convex hull. There's no reason a priori that they have to be one containing the other, but this turns out to be true. The second point, B, it's actually not hard to verify from the picture. It's just saying that these slopes from L0 to L1, from L1 to L2, and so forth, these are increasing slopes. Well, that's just by the definition of the convex hull. And the third point is that, well, these quotient lattices are very well behaved, meaning that they have determinant 1. Well, determinant 1 is just because I'm normalizing by the RIs, which are these normalized determinants. And the interesting part is that all the sublattices of these quotients also have determinant at least 1. So this is a well-known theory of lattices from the 80s that we're going to be using. Well, a more interesting development that happened in the past few years was that such lattices that have determinant 1 and sublattices all of determinant at least 1, they're called stable lattices, and they're actually very, very useful, in part because of this theorem of Regev and Stephen-Savidowitz. Again, if you haven't seen this, it's not so clear why this might be useful. But the point here is that, well, there's this theorem of Minkowski that's very well known, that if you have a convex body that's symmetric and has like large volume, at least 2 to the n, then it has a non-zero integer point, right? This is kind of saying an opposite statement, meaning that, you know, if a lattice is sparse in every sublattice, then it cannot contain too many short vectors in a way. So the point is that this summation of exponential of x squared is kind of measuring how many short vectors there are. Like if you have too many short vectors, then the summation will be large. But, you know, if you only have a few short vectors, then there won't be too many contributions beside the origin. So like when x equals 0, the summation already gives a 1. But, you know, the point here is that everything else will give at most half. And so this was shown for this parameter s to be log n. There's not a very good reason why this should be log n. For example, like if the lattice L is the Zn, we expect this to be a square root log n. But so this is still an open problem whether this log can be improved by square root log. Like essentially, like Rig, Evans, Stephen Davidowitz, they conjectured that the maximizer of this discrete Gaussian sum is exactly the integer lattice, but this is still open. So this theorem was already used before by Dadouche and Regev. They showed that this implies this subspace flatness conjecture, you know, that you can approximate this covering radius up to a log factor for ellipsoids. This was known a while ago. And so we're going to be calling a lattice stable if it has this property that determinant is 1 and all the determinants, all the subdeterminants are at least 1. So notice that this reverse Minkowski theorem works on not only for stable lattices, but for everything that has determinant at least 1 for all sublattices. So the idea of our proof is that we're going to be using the triangle inequality. And, you know, when we use the triangle inequality, we're going to be finding a chain. So we take this chain of these, this canonical filtration, and we apply the triangle inequality for every step in the chain. And the nice thing is that all of these quotients are going to be, well, they're not necessarily stable, but they're scalings of stable lattices. So the determinant is not necessarily 1, but, you know, it still has the property that all the sublattices are sparser. And then we're going to end up with this weird projection onto the orthogonal complement of the span of this intersection, but it turns out to be not too bad. So the idea here is that we're going to need a way of bounding this covering radius of some convex body with a stable lattice. And for this is where we need the reverse Minkowski theorem. Well, I won't give the full proof of this, but the point is that we're going to use the reverse Minkowski theorem together with some machinery of Banach from the 90s to show that, you know, if you have a stable lattice L and any symmetric convex body K, then you can upper bound this covering radius by, well, it's essentially by this L function of K, which is sort of like the average thinness of the body, meaning like I sample a Gaussian and I look what is the norm with respect to this convex body K on average. So there's this log factor that we need to pay. I'm really not sure if this log factor is necessary. For example, if the stable lattice L is just the integer lattice, I think we can show that this is true without the log factor. And in general, we don't have any example where this log factor is necessary. But, you know, for the proof, there's a reverse Minkowski theorem that we use. That's where the log factor comes from. A priori, it's not clear whether this log is necessary. So in order to deal with this projection of a section, we're going to use this lemma, which is actually quite simple. It's just saying that, you know, if you have any projection over any like intersection, this is not going to increase your L function. The point here is that you just need to show this for sections, actually. And the reason why this is true for sections is it's just a Jensen's inequality. Like essentially, we want to deal with this Gaussian. Well, we can split the Gaussian into the Gaussian restricted to the subspace and the Gaussian on the orthogonal complement, and just use Jensen, essentially. It's not too hard. And the fact that it also works for projections Well, the point is that a projection is larger than what you'd get from taking a section. So let's see what we get. So if we apply this this lemma and these two lemmas together to the equation above, to this triangle inequality, then we just get this log n times the L value, the L function of k, times the sum of these normalized determinants. That's because, well, this lemma only applied for stable lattices, and here we have like some scaling of the stable lattice. So that's why we need to pay this Ri from 1 to I star. So recall that I star is whichever part of the partition of the canonical filtration we're choosing. So now if we want to upper bound this covering radius, we essentially just need to understand how to upper bound these normalized determinants. So recall we had this inequality, and so here we're going to need some kind of subspace. Well, the subspace we're going to take is just an orthogonal complement of the span of like essentially half of my canonical filtration. So here the point is that we're going to use the normalized determinant. Well, it's actually at most what you'd get from projecting the entire lattice onto this W. Well, this is just following from the fact that these normalized determinants, well, essentially the determinant of this projection of L can be written as a product of these quotients. So this is essentially just a geometric average. It's using the fact that Ri star is the smallest among the following ones. And now I can just multiply and divide by the volume because, you know, I wanted to have this quantity appear somewhere. And now we're going to have to relate this to the L value somehow. So we do this by using this classical inequality in geometric analysis called the Wilson inequality. So it essentially says that among all bodies of the same volume, the Euclidean ball has the least width. And you know, it turns out that the width is related to the polar of the L value of the polar. There's this factor of over D here, and that's related to the volume of the unit wall. And now we just use the previous lemma to upper bound this L of the section with the L of the polar body. So to recap, what we showed is that, you know, we had this inequality here from the triangle inequality. We can, well, the thing is that we're going to need a subfiltration here. So we had this canonical filtration. We're going to essentially have to group all these sublattices so that these ratios are going exponentially. This would just make things easier because now I had the sum and I can just upper bound it by the largest one. So essentially what we got is that by the previous slide, we have this log n times Lk from the lemma, and then we get this Lk star from like the Wilson inequality, and then we have this 1 over D factor. So now we're going to be able to upper bound this LL star product by this classical theorem of Figuiel, Jagerman, and Pissier. This is saying that like for any symmetric convex body, we always have some invertible linear map. For example, that makes it kind of like well-rounded. For example, like imagine your convex body could be like very flat in some direction, and it kind of just shrinks that direction somehow. We also don't know if this log n factor could be improved by square root log n. I think square root log n would be tight, for example, if you had a cube. And also I would like to mention that for general convex body that's not necessarily symmetric, I think it's still open whether this can be done up to an n times polylog factor. So here I'm kind of so here I'm only showing this theorem for symmetric convex bodies for now. Recall that like I'm just going to go back a few slides just to show you what I was showing. So here I'm claiming that it works for any convex body K, but we're only showing this for now for symmetric convex bodies. So that's why we can actually use this this theorem. There's another part of the proof that deals with the case where it's not symmetric, but I'm not going to talk about that now. And so the point here is that if I take this I star, which is the part of the canonical filtration that I'm choosing, if I pick it so that the dimension is at least half, well, it also implies that this d, which is kind of like the suffix, is also at least half, because I'm taking it so that it's a minimal, so that it's half. Well, so the previous one is less than half, which means the d, which is the suffix, has to be at least half. And the reason why I need d to be at least half is that if you look at this inequality above, I have a 1 over d that I want to cancel out of this n factor. So let's recap. We had this L position where we put k in. Notice that this doesn't change the determinant or the volume. We use this triangle inequality to upper bound this covering radius. So we had, well, we had the other term with the projections that we can deal with by induction. Since the dimension of u is at most half, well, the dimension of u is at least half, the dimension of the complement of u is at most n over 2. And that's why we can deal with by induction with the second part. This first part, we pay this log squared factor from the previous slide. And then to conclude, we just need to note that the log squared plus log cube of n over 2, that's at most log cubed. So essentially, if you think about it, the way the proof works is that, well, we put k in the L position, then we find the subspace U, and then we kind of recurse on this other projection, meaning that we look at the other projection and we put that again in the L position, and we keep doing that. So this has like log n many rounds. So notice that here in the theorem, I wrote that it's symmetric convex K. So it's cheating a little bit. In the full proof, we need to use a symmetrizer instead of K, meaning we take K intersect minus K when K has is translated so that the barycenter is at the origin. But for now, I'm going to simplify things and we're just looking at the symmetric case. That's why we can put this L position so that it's at most n log n.
Victor?
Yeah.
You say you take a self-filtration so that the ratios of the determinants grow exponentially?
Yes. Yeah, essentially like this canonical filtration, it doesn't guarantee anything about the RIs, and rather that they're increasing, right? So we don't necessarily know that a priori. However, what we can do is that we can kind of make subintervals of this filtration and collapse them together. So essentially, we just take a subsequence of the canonical filtration.
And this is always possible?
Well, we can always take a subsequence. There are a few things we need to argue is that whether, it will also have these nice properties that the determinant of the sublattices will be lower bounded. And, so what we end up using is like some approximate filtration, meaning that, well, the sublattices won't necessarily have determinant at least 1, but, they have determinant at least like 1/2.
Mm-hmm.
Well, a normalized determinant at least 1/2, let's say.
Mm-hmm.
So yeah, it takes some work to argue that this is always possible, that we can always group things together. It's not super interesting. Yeah, essentially this is necessary just because, we end up with the sum of these normalized determinants, and it's much easier to deal with a single one of them than to like deal with all of them. If the sum is, if they're like growing exponentially, like 1, 2, up to 2 to the I, well, the 2 to the I kind of dominates the entire sum. So I'll mention a couple applications of this. I also had a slide to talk about the generalization to non-symmetric convex bodies. Okay, so the point here is that I translate K so that the barycenter is at the origin. And, so the point here is that we need to bound this volume of the projection in terms of the volume of the projection of the symmetrizer. And this turned out to be a tricky inequality. Well, it's essentially like a polar version of Rudolphson's inequality for sections. But it also takes some other work due to Fradelisi and others to get this to work. So I won't spend too much time on this technical detail. So there are some other implications of this result. For example, if I have a covering radius of an asymmetric convex body K with respect to a lattice, I can upper bound that by the covering radius of the symmetrizer, like this I guess difference body, K minus K, up to a log cube factor. Well, this is because I can upper bound the covering radius by that lower bound, this projection. And the point is that, well, if I take the volume of K minus K, turns out that that's at most the volume of K up to an exponential factor. That's an inequality of Roger-Shepard. And, once you normalize that, it turns out that, you get this inequality pretty much freely from the main theorem. So there's another consequence. It's this flatness constant of convex bodies. So here, the quantity that is studied is that if you have a convex body with that has no integer points, then there's always a direction for which this I can fit all these points in K with these hyperplanes with an integer direction up to n to the polylog. And previously, the best known bound for this was n to the 4/3 times the polylog due to Rudolphson. And note that here it suffices to show that this covering radius times the shortest vector of the polar of the dual lattice is at most n to the polylog n. Well, this is because if I have a convex body K that has no intersection with the integer lattice, then the covering radius must be, well, it's at least 1. Because since it doesn't have any integer points, then I need to scale it at least 1. So the point here is that, well, Bonachik showed a bound of n log n for symmetric convex bodies in 95. And what we do is we just use the previous theorem with the covering radius of K minus K to bootstrap this into this. Essentially, we just pay another log factor from Bonachik. And I would like to mention also that Daniel Dadouche found a stronger version of this statement, because he showed that essentially this flatness constant is upper bounded by n times the subspace flatness constant by using Minkowski's theorem. So this is only a slightly more difficult proof. So I would like to mention just a couple open problems. Well, here I showed an algorithm that ran in log n to the 4n for integer programming. Well, we still don't know whether every integer program can be solved in exponential time without the log factors. So this approach doesn't work because the flatness theorem that I showed you, there was a log cubed. Actually, you cannot do better than log. It turns out that there's a simplex in n dimensions if you take the convex hull of E1, 2, E2 up to n times En. So that's a kind of simplex with different side lengths. It turns out that the best you can do for that one is a log n. So you cannot hope to do better than log n to the n with this approach. But there's no reason why you couldn't just solve every integer program in exponential time. At least we don't know any hardness results. Another interesting another interesting open problem is this type reverse Minkowski. It's essentially asking, okay, if I have any stable lattice, can I show an upper bound on the discrete Gaussian that's at most the integer version? So here S is any parameter. And I think in their original reverse Minkowski paper, they show that this works for a very specific range of parameters S. I think for n at most 4, this is known, but for at least 5, it's still an open problem. Okay, thank you for your attention.
Thank you, Victor. Are there any questions, remarks? These questions regarding solving integer problems in exponential time, are they still applicable? Or is it more of a theoretical interest? What's the barrier?
So I would say it's more theoretical. Like in practice, people use like branch and bound and like other heuristics. But it's interesting because, for example, if you look at like the satisfiability problem, you can always solve it in like 2 to the n by trying like every variable can be either true or false. So, you can solve it in 2 to the n. If k is an ellipsoid, people also know how to solve this any integer program where k is an ellipsoid in 2 to the n by using the Voronoi cell. So that's a very specific tool because, like in general, Voronoi cells are not necessarily convex for any norm, but for the O2 norm, it is known how to solve in 2 to the n. And even for LP norms for p different than 2, it's still open whether you can do it in 2 to the n as well. But yeah, I'd say it's more of a theoretical interest. Of course, if it was a simple algorithm, then that might be practical. But
well, the LP norms, you said nothing is known besides p equals 2, or do you know for p equals 1, p equals infinity?
For p equals infinity, I think there's an approximate version of IP that can be solved, but I guess in general, I don't think anything is known as better than just this log n to the n for p different than 2 for the exact problem. Yeah,
I see.
Because the point is like, even if I have a cube, well, this algorithm, for example, requires me to project the cube somewhere and take sections of my cube. So I end up with like much more complicated convex bodies after a few iterations. So I lose much of the structure after a few rounds.
And the projections and sections here are not, it's not constructive, right? It's everything. There exists some projection that works.
Well, so the point is that like, so here I wrote that, this, that there exists some canonical filtration, right? Like the way I defined it, it's very much not constructive because, there's no way I can list all the sublattices and construct this canonical filtration. But there was a paper of the Douche from 2019 that he described how to construct an approximate canonical filtration, where I have this property that all my sublattices have determined at least like 1 over log n. Like I said, the normalized determinant at least 1 over log n. That can be done in randomized polynomial time. Well, it's randomized exponential time. And it's also using this reverse Minkowski machine learning.
I see.
So yeah, I can construct it, but it's a little slow. Yeah.
Any other questions, remarks? This improvement in the logarithm by the Douche, is it published now, or is it something?
You mean in the
log 4 with the reverse Minkowski? Oh no, Minkowski's theorem.
Yeah, so this is in the latest version in our archive. Yeah. Okay. It's not too complicated. Essentially, like, it's just a few lines. Essentially, it uses the like the what's it called, the Blaschke-Santalo relation between the volume of K and the volume of K polar. The point is that here in the main theorem, I have this expression that's like a determinant over the volume. Well, it turns out that I can also rewrite this in the dual form, meaning like I can write the volume of the polar intersected with W and like the determinant of like the dual lattice intersected with a subspace. And it turns out that if you look at that and you think about what happens to the short vectors, that there's a simple inequality you can write too.
I see. Any more questions?
Yeah, I can also mention that like in this flatness constant here, yeah, we don't know anything better than n. Essentially, like it could be that the flatness constant is just a linear. That's still an open problem as well.
Nice. Okay, if there are no more questions, thank you, Victor, again. And see you all next Monday in another poll session.
Yeah, thank you.